the second for the second session. So now we will have from the theoretical input. So first we have Jo Dudek, who will talk about the light meson spectroscopy from Lattice QCD results. So please start. So when 2 minutes will left, I will let you know. Okay.
Okay. Can you hear me? Okay.
Yes. Yes, we can hear you very well.
All right. Yes. So I was asked to present something on the physics of light meson spectroscopy using Lattice QCD as a tool. And I've chosen to focus on what can be said about resonances. In particular, these are really the systems that are of most contemporary interest. And I'm going to try to argue that Lattice QCD can resolve these things as they actually appear in experiments as decaying systems, not having to sort of pretend they're stable, for example. So as you no doubt know, Lattice QCD is an approach to QCD where one takes the fundamental theory, places it on a space-time grid of finite size, and by Monte Carlo sampling configurations of the gluon field, one can get at physics by computing whatever correlation functions you're interested in, averaged over this set of gluon field configurations. So of course, in doing this, you've made a number of controlled approximations. Let me remind you what they are. Of course, you have to discretize the action. So you have to make a choice of discretization, and you have to choose a finite non-zero lattice spacing. I'll argue that for the quantities I'm going to show in this talk, that's relatively unimportant. If you really care about high precision, you've got to get complete control over that. But for what we're doing, that's not going to be the major driving factor. Another feature you have, if you like, is that the quark masses that appear in the Lagrangian are free for you to choose. Ideally, ultimately, you choose the physical values, but you're free to turn that knob and examine how QCD behaves as a function of quark masses. So that's something we like to do. And finally, you put your theory inside a finite space-time volume. And what I will attempt to show you is that actually that finite spatial volume is a tool that you use to access scattering amplitudes. So if you're interested in spectra, then what you want to compute are 2-point functions. Here's an example in the top right. So these operators here are constructed out of quark and gluon fields to have overall the quantum numbers of whatever system you want to look at. And you can see on the right-hand side here that in the Euclidean spacetime, this is given by a sum of decaying exponentials, where the decay rates are controlled by the energies of the states you're interested in. So the simplest thing one can do is go to large times, and then this sum is going to be dominated by the lightest state with those quantum numbers. And so you can get rather precise results for the mass of the lightest state in each quantum number, in particular if it's a stable particle. But as I said, I want to convince you that we can get at resonances. So how do we do that? Well, first of all, we should remind ourselves what we mean by a resonance, and we can illustrate that most easily with one-dimensional non-relativistic quantum mechanics. So here's some simple-minded potential, and you can easily imagine that were you to solve the Schrödinger equation for this potential, you could get some discrete bound states, and then of course a continuum of scattering states for positive energy. And if there's a resonance, you know that this will appear most likely as a bump in that continuum and would be characterized by something like a rapid motion in the phase shift, which describes the wave function outside the potential. So of course, the point is that resonances lie in a continuous spectrum of scattering states. But what I just told you is that in Lattice QCD, we'll be extracting a discrete spectrum of states. And of course, the simple reason for that is that we're working in a finite volume. And as soon as you work in a finite volume, you're applying some boundary conditions at the volume's edge. And that additional constraint is going to quantize the scattering continuum into a discrete spectrum. So you can see that in quantum mechanics, if you apply a periodic volume in your one-dimensional system, i.e. put it on a circle, it makes the continuum become discrete. But here's the core point: that discrete spectrum is sensitive to the scattering phase shift as a function of energy or momentum. So you have this simple equation in the bottom right-hand corner relating the discrete energy levels to the phase shift. And the point of the lattice QCD approach is to run this backwards, to compute the discrete spectrum out of correlation functions and use that information to infer what the scattering amplitude is. Now, of course, one has to do this not in one-dimensional non-relativistic quantum mechanics, but three-dimensional relativistic quantum field theory. But the corresponding relation was long since derived by Martin Lucia and polished by others later. So the formalism conceptually is the same as what I just described, although technically somewhat more complicated. So here are some examples of this at work. Here is the system of 2 pions in isospin 2. And on the left here, you see the little black dots are discrete energy levels computed on 3 different lattice volumes in a lattice QCD calculation where the light quark mass is chosen so that the pion is about 400 MeV. And so you see these spectra in the rest frame and several moving frames. And the point is, by pushing these discrete energy levels through this formula, which relates them to discrete points on the phase shift curve, you get the S wave and D wave elastic isospin 2 scattering phase shifts shown on the right-hand side. And as you would expect in this isospin 2 channel, this is a mild repulsive scattering with no resonances. But this illustrates the sort of philosophy of the approach. If you move to isospin 1, now in a P wave, again on the left, you see some discrete energy levels, the extracted spectra from a lattice QCD calculation. And once pushed through this formula that gives you the phase shift curve, you get the data on the right. And you can clearly see this is the behavior of a narrow resonance that you would interpret as being the rho at this heavier than physical quark mass. You can do the same calculation again with somewhat lighter quarks and hence a lighter pion mass. And you see, again, something very similar. But if you examine this carefully, you'll notice that the rho has become lighter. The phase shift is moved central, but the center of the phase shift rapid motion is moved to a lower value of mass and has become broader, which is precisely what you would expect given the increased phase space for this decay. Finally, for elastic scattering of pi, here's the isospin 0 case, much the same story as regards the calculation. And then on the right-hand side, you see the phase shift curves. And here you notice quite an interesting transition between the heavier pion mass, 400 MeV in green, and the lighter pion mass in red. And this transition represents, in fact, the sigma transitioning from being a stable bound state at the heavier pion mass to being much more like it is an experiment of broad resonance at the lower pion mass. Now, I've rattled through this because this is really just to illustrate how this works in the simple case of elastic scattering. But for the vast majority of interesting hadrons, they are coupled channel states. They decay into more than one final state. So this is what I really want to linger on a little bit. So ideally, what you would like to know in a coupled channel system is the T matrix. So for a given partial wave, you'd like to know the scattering amplitude as a function of energy from each possible initial state to each possible final state. And if you can get this quantity T of E, this matrix T of E, then once you've got it, you can do all the things you would ideally do with a T matrix obtained from experiment, which might include analytically continuing to complex energies to look for pole singularities, which you would which can be argued are the least model dependent way to describe resonances. So of course, what we actually have access to is the finite volume spectrum from a lattice QCD calculation. And I show here in the red box the equation which relates the two. So you see what you've got in the square braces here is a matrix. And in that matrix is the phase space, which is a relatively simple known quantity, the T matrix, which is what you want to know, and a matrix here, M, which is a function of both energy and the volume in which you work. And this is a bunch of kinematic functions that you know. They reflect the shape of the box, essentially. So the idea here is if you knew what T of E was, you could compute this matrix and take its determinant, and that gives you a function of E. And every place that function of E crosses 0, that is a discrete energy level in the finite volume that you chose. Now, of course, you run this backwards. You don't have T of E. You have the discrete finite volume spectrum, and you need to infer T of E from it. So what has proven to be a powerful way to do this is to parameterize the T matrix as a function of energy. For any given set of parameters, once you fix them, you can solve this problem and obtain a finite volume spectrum, which you can then compare to the one you got in a lattice calculation. The difference between those defines a chi-squared, and you can then vary the parameters in your parameterization until the chi-squared is minimized and your two finite volume spectra, your model one and your lattice QCD computed one, are in agreement. And that's your best estimate for the finite volume. It's your best estimate for the scattering matrix. Now, you might worry that by doing this, you're introducing bias because you parameterize T of E, and of course, that's absolutely right. You can do that. So our approach has been to try many parameterizations and examine which features are essentially independent of the details of the parameterization. So let me show you some examples. Sticking with this 400 MeV pion mass, here is coupled channel pi eta kk bar scattering in S wave. I'm not showing you the energy spectra or how we got to them, but once you analyze them, this is the these are the elements of the T matrix you get. In red, pi eta to pi eta, in orange, pi eta to kk bar, in green, kk bar to kk bar. And you see there's this rather sharp asymmetric peak at the kk bar threshold in pi eta goes to pi eta, along with rapid turn on of kk bar final states. And sharp features like this are typically associated with resonances. And indeed, if you analytically continue all parameterizations that are capable of describing the finite volume spectra, you find indeed that there is a pole singularity relatively close to the kk bar threshold. From its position, you get, well, its position. From its residue, you get the couplings of that resonance to kk bar and pi eta. And here they're shown, they're of roughly similar magnitudes. So this you would associate with some sort of heavier quark mass version of the A0 980. In the isospin 0 channel, something similar, pi pi, kk bar, eta eta, but you see that the structure of the amplitude looks completely different. The pi pi goes to pi pi has a sharp dip at kk bar threshold, while kk bar still turns on rapidly. Nothing happening in eta eta. What you find is happening here is that you have this bound sigma that I talked about before, and an F0 980 like resonance just above kk bar threshold. And the sort of constraints of elastic unitarity force this dip on you here. Sometimes the resonances do look like very simple-minded, Breit-Wigner style behaviors in the D wave of pi pi kk bar. You see here two peaks, one dominantly coupled to pi pi, one dominantly coupled to kk bar. And these look an awful lot like the F2 1270 and F2 1525. Now, these are all the first calculations of their type. One can imagine that a next round of calculations will vary the light quark mass, and you can track these poles around the complex plane as you vary the light quark mass, and hopefully that teaches you something. Now, you're not, in fact, restricted to pseudoscalars in the scattering process. You can have scattering particles of non-zero spin, and here's an example. If you work, excuse me, if you work at heavier than physical pion mass, for example, the omega and phi mesons become stable, and then you can scatter them as stable particles. And here's an example of pi omega, pi phi coupled channel scattering. And here you see a clear peak corresponding to the B1 resonance. And in this case, once you start going to non-zero spin scattering particles, then you can have multiple partial waves contributing to a single JP. And here, down here, you see there's both S wave and D wave. So this is somewhat analogous to the deuteron system. But again, you can completely constrain the coupled channel T matrix, and there is a resonant pole here. And you can get at the couplings to the different partial waves here. And these are in principle something that can be measured, for example, at GluX, and were previously measured at E852. Not quite in this way, but in a similar way. Here's another example. In this calculation, we ramped up to, we ramped the light quark mass all the way up to the strange quark mass to render there an exact SU3 flavor symmetry, which somewhat simplifies calculations by coalescing various decay channels into one. And what I show you here is pseudoscalar vector scattering in 3 JPs, so 1 minus, 2 minus, and 3 minus. And what you see is something rather nice, that you see different behaviors in each partial wave. In spin 3, you see this nice sharp resonant peak, which corresponds to a pole very close to the real axis. In spin 2, which is coupled P wave, F wave, you see a much broader resonance, which is way out here in the complex plane. And then in spin 1, as you might expect within the quark model, you see 2 resonances. A lighter one, which is somewhat broad, and a heavier one, which is very close to the real axis, leading to the sharp dip-like feature. So this is to illustrate that this finite volume lattice QCD approach is quite capable of dealing with narrow resonances, with broad resonances, and with strongly overlapping resonances. So it really seems to be a quite broadly applicable tool to study resonant systems directly in first principles QCD. So a rather interesting case we looked at recently was the exotic 1 minus plus channel. So here, again, we're working up at this SU3 flavor point where the light quark masses are equal to the strange quark mass. And here's the spectrum that we obtained from which we will constrain the scattering amplitudes. So in this case, we're just using the rest frame for reasons I can explain if you ask, but we're doing so at 6 different lattice volumes. Each of these points is going to serve as part of a constraint on what turns out to be an 8-channel scattering matrix. So this is a rather complicated multi-channel scattering problem. Nevertheless, we are able to describe all of these energy levels and get an 8-channel scattering matrix and examine its pole content. And we find that it does indeed have a pole singularity at about 2.1 GeV with a very narrow width. There appears to be a very narrow resonance at this quark mass with 1 minus plus quantum numbers. When we examine its residues to get at the couplings, what we find is that it has relatively small couplings to what you would think of as the SU3 version of pi eta or pi eta prime rho pi, but significant couplings to pseudoscalar axial. So for example, things that would look like pi B1. And that's sort of rigorous at this heavy quark mass. We did attempt, excuse me, a crude extrapolation down to physical kinematics, but because I have limited time, I won't show that. You can ask me about it afterwards if you're interested. Now, it's not just the case that we can consider hadronic scattering processes. Another interesting extension of this finite volume formalism is to couple these resonant scattering systems, or indeed non-resonant scattering systems, to production amplitudes, where one has an external current. So here are a couple of examples in which the external current is a photon, a vector current. One where you directly produce pi. So this is somewhat like what you would get in E plus E minus annihilation, or a slightly more challenging case where an initial lone pion absorbs a virtual photon to produce a pi scattering system. And of course, as must be the case, any resonance that appears in pi goes to pi has to appear in this production process. And there you see the rho. But of course, what we can do here is study the dependence on the photon virtuality. And that's what's shown here. And furthermore, we can take this amplitude, analytically continue it to complex values of the pi scattering energy and go to the rho pole and extract what you would hopefully agree is the least model dependent definition of the pi gamma rho transition form factor. And this is an interesting, this opens up an interesting possibility of computing not just things that can be measured in experiment, but things that can't easily be measured. So for example, one could use this technology to study scalar meson resonance form factors with vector current or other currents, analytically continue to the resonant pole and study the virtuality dependence. And the idea is that might inform us something about their physical size and or flavor content, and could hopefully be a first principles QCD entree into questions that have been raised about their internal structure, for example, whether they're tightly bound objects or whether they're much larger molecular style objects. So those sorts of calculations haven't been done yet, but you can hopefully see how one would go about doing that. Now, everything I've shown you so far is systems of two mesons, and we of course need to go beyond that. Most interesting resonances decay into three-body or higher final states. The way the finite volume formalism works is if a three-body final state is kinematically open, you can't ignore it. You have to include it in your T matrix. And the formalism, the formalism I've shown you so far is restricted to two-body scattering. A formalism to describe three-body scattering in finite volume is significantly more complicated and has been in development for over 10 years. But those formalisms are now in place and are being applied to actual calculations. And here's an example of 3 pions in isospin 3. So again, a non-resonant system carried out by some colleagues of mine, where they're able to do the full workflow all the way from calculating the spectrum through describing the finite volume behavior, all the way through to a significantly more complicated process than in the 2-to-2 case, all the way through to the three-body scattering amplitude with all its sub-channel possible dependencies embedded in there. So this is really exciting. In the near future, you should expect to see more calculations of this type in resonant channels. We've seen the first of those describing the A1 by the George Washington group, albeit with probably not as much constraint as you would really like. I think we'll be seeing much more in this direction very soon. So I think I've managed to keep to time, unusually for me. I hope I've given you a little bit of a flavor that Lattice QCD has evolved in such a way that it's becoming a practical tool to study excited hadron resonances in a really pretty rigorous way. It's somewhat currently limited to heavier than physical quark masses, largely not for computational reasons, although that's part of the story, but mostly to avoid the resonances you're interested in decaying into many body final states where the formalism is not quite ripe yet. But we can still learn a lot about strong QCD, particularly the behavior of strong QCD a little bit away from the physical light quark masses, where previously we were entirely reliant upon models which had, you know, of undetermined relation to QCD. And so I hope that what we've seen over the past few years is the start of a new era of hadron spectroscopy, really fundamentally based in QCD. So thank you.
Thank you. So now the floor is open to the questions. So, okay, yeah, Christopher.
Hi, Joe. Thank you very much for this excellent talk and congratulations for the beautiful results. I have one question regarding your T-matrix parameterizations. In particular, since you raised interest in studying the quark mass dependence, you say you want to construct your T-matrix in the most unbiased way, but would you call it biased to impose chiral constraints more rigorously? Because as far as I understand, you basically write down a general K-matrix ansatz and just see what you get. But imposing chiral constraints could be useful here, and in particular when it comes to studying the quark mass dependencies.
Yes, and of course you're right. As you go to lighter quarks, there's more benefit from doing that. I think it's not totally clear to me that working with 400 MeV pions, there is a significant benefit to building in chiral constraints. And of course, it's not as unique. It's not entirely unique, especially when you're considering high-lying resonances, whether those chiral constraints actually really do anything much. There are examples where this has been done by others. So the A0 calculation, some of your sometime co-authors did an analysis building in some chiral constraints of this data. And after they corrected an unfortunate numerical blunder, the results were essentially exactly the same as the range of K matrices that we used. As you go to lighter quark masses, there certainly are benefits to considering whether whether spontaneously broken chiral symmetry offers additional constraint. In particular, in cases like the isospin 0 channel, where the sigma is going far into the complex plane, it's pretty likely that more constraint will be required than can be directly provided by actually, I'm slightly misspeaking there. The lattice constraint offers significant constraints, something like dispersion relations, which build in crossing. Whether or not that's explicitly using chirally motivated modeling is another question, but certainly more constraint than just the finite volume energy levels is probably required.
Well, actually, just a side remark, and then I'm done. It's extremely difficult to use a K matrix to describe the sigma for physical pion masses, where people really have to be very careful there, and usually it goes wrong as long as the chiral constraints are not properly built in. But this is just basically along the lines of what you said anyway. Thank you.
Okay, Patricia, please.
Hi, thanks, Joe, for a nice talk. I'm just getting a little bit puzzled about how do you extract the pole position, like for instance in this light scalar sectors, because as I understood, like you get the phase shift from like inverting that other relation, and then but this is still like discrete. So how can you manage to? Oh, it's not,
no, so look,
so I get it wrong.
Look at this. So the point is here, you parameterize T as a function of E. So at this point, this is a known function. This is a known matrix of functions, right? As Christoph said, it's typically embedded in by a K matrix formalism. So what comes from the finite volume energy levels is the parameters in here. But this is a function, so you can analytically continue it in the same way you would any other function by just
and
taking
any other function. Okay, so it's completely standard the way that you just extract. Okay, cool, nice, thanks.
Okay, Beijiang.
Okay. Hi, Joseph. On the results on page 18, is it about, sorry, I mean, lost my focus. Is it about the 8.1 or the 8.8?
Yeah, so this is, excuse me, this is the octet state. We haven't yet computed the SU3 flavor singlet state. So what we did, let me show you the extrapolation. So realize this is crude and could be wrong. So I'm making a separation between the results of the lattice calculation that are almost certainly correct, unless we made a blunder, to things which are imposing additional physics. So this, we can use the octet result to make a statement about what the pi1 behaves like at physical quark masses, but not the two eta ones, because we don't have the singlet. And the eta ones are going to be admixtures of the singlet and octet basis states. So until we compute the singlet, we can't make a definitive statement about the eta one, which is just telling us that we should get on with computing the singlet.
Okay, thank you.
Okay, thanks, Joseph. I think other discussion can carry on in the discussion session. So thank you again. So next, I think we